This video is being sponsored by Educative.io, which has a collection of well-written crafted courses for software developers, from Python to front-end to system design to scalability to Docker and whatnot. Learning at Educative is really powerful because they have all coding workspaces in the browser itself, and also they offer Educative Unlimited, in which you pay only once for all the courses. They have annual and monthly plans, and my audience gets a 10% additional discount on the 40% campaign they have for India. So you get a 46% discount on using the coupon Rachit, and you can have the link in the description below. So far we had discussed what is distributed data and what does it mean in terms of replication versus partition. We also saw various replication architectures. We discussed single leader in detail. We discussed how leader is handling the writes and it's having a synchronization algorithm which is actually performing the replication. We also discussed synchronous and asynchronous replications. We discussed various scenarios like if leader is going down, what if the replica is going down. And we also discussed how replication logs work. We also discussed the problems associated with replication lags. So we have covered quite a lot, but now it's time for us to understand what if single leader is not enough and it's time for multi-leader replication. To be precise, when you are talking about multi-geographies and your application is quite huge, you cannot just deal with one leader which is present in some data center. You have users in different geographies, and if you just have a single leader, it does make things easier because there are no write conflicts, as we will see in multi-leader replication in just few minutes. But the biggest problem is the network latency that your users will face. So it's not scalable for your application to have different geographies users but a single leader. So once you are going beyond data centers in one geography and you have data centers all over the world, it's time to also have at least one leader in each data center. And this is how it used to work in single leader configuration. One leader and all the followers are having a replication algorithm going on. But in multi-leader replications, there is L1 and L2, and L1 is having multiple followers. For demonstration purpose, I have just taken one. Similarly, L2 is having its own set of followers. But now L1 is not just syncing to the followers in its data center, but it's also syncing, or it's also performing replication all the way to the different data center, and it's using the leader L2 and having a replication closed loop cycle with L2. Similarly, L2, which is having its replication with the followers in its data center, it's also doing a replication beyond data center to L1, which is in different data center. So this is how it's going to look like, and these blue signs is something which differentiates multi-leader replications with single leader one. There is replication also happening between leaders of different geographies. In this case, I have just taken two, but as we will see, if there are more than two leaders, this topology of how this replication is working is also important. So what is the benefit of multi-leader replication? Well, as I've said, the network latency is something which will be very, very huge if you are having across data center communication. So this is why in multi-leader configurations, every user can have its writes redirected to the leader of its data center. So network latency is something which multi-leader enjoys, but single leader suffers from it. Also, just want to make sure that many databases already implement this replication of multi-leader by default. However, having said that, there are also third-party tools like Tungsten Replicator for MySQL, BDR for Postgres, and Golden Gate for Oracle. So you can integrate with these tools as well to support the multi-leader configuration. But as I'm saying, in multi-leader there are conflicts. So let's talk about that in a very simple example. So let's say there are two different users across different data centers. So this user A, it's communicating to L1 and it's saying that change title to A. Similarly, this other user is saying change title to B. And these L1 and L2 both will say to the user, okay, I have accepted your right. But when it's time to perform that blue arrow, which was about cross data center replication, these blue arrows. So when these happen, this is the time when you actually realize that, hey man, there is a conflict. So when this replication goes to L2, that user is requesting the change of title to A, this will reject it. It's saying that the title now is B. Similarly, when this particular replication is sent from L2 to L1, this will be rejected. So this is the place, or these blue arrows that I have shown above is the place where you are actually detecting the conflicts. Now once you are detecting them, you have to solve them. But before, like, how do you detect there is a conflict? So let's talk about that for a few minutes. So in single leader, this case wouldn't happen. Why? Because, well, you have just one leader, so both writes will come to it. And when second user is trying to perform a write, we can actually say that there is already a write happening on this particular row. So you can either wait or we are going to abort it. So single leader, it already knows that there are two writes happening. That's not the case with multi-leaders. So that's why it's tricky. In multi-leader, the problem is L1 at that time when user sent the write request, it responded back okay to the user, right? So you are having that confirmation given to the user in both the places. And now it's just during the replication, you are actually detecting the problem. So in the replication, the problem is detected. So in single leader, you can say the writes are sequential and the last write can determine the final value. But in multi-leader, that last write is very, like, you can say it's controversial, because in L1 the value was A and the new value is B, right? So if it accepts the last value, L1 will say the last value is B. However, for L2 it was having the value B and during replication the last value came was A. So at this point, if you just accept, like, for every leader you are saying just accept the last write, well, different leaders will end up with different values. So your database is in a corrupted state. L1 in its data center is saying the final value is B, and L2 in data center 2 is saying the final value is A. So this is where we want consistency. We want that both should converge towards a final state so that the database stays not corrupted. It should stay the same in all the regions. However, it may take time, but the final goal is to converge to the same value for all the leaders. So one example to do that is if you also capture the timestamp for every write. So let's say the write A had happened at T1 and the write B had happened at T2. You can say that instead of saying last write, we can actually say the higher timestamp wins, and this is still better. So this is one way. The other way is you can say let's merge values. Let's store both A comma B and let's show both as comma separated values. So that's another case. So basically it depends on your scenario, whatever thing. So basically if you're working on a cart, if you had received product A from some place and product B from some place to the same cart, this second approach makes more sense at that point, right? So it depends in what scenario we are. We have to pick different strategies to resolve conflicts. But the main stress that I want to highlight is in multi-leaders, there is always a conflict which may happen during writes, and you have to determine how to resolve that. Also, there is another strategy in which you can record the conflicts as a separate, in a separate data table or as a data entry. And then the application code can actually show to the user that these are the last conflicts that we have detected and please resolve that. So CouchDB is one example that follows this particular strategy. Also, all these conflicts detection and everything, it's happening at the row level. So if you have a transaction dealing with multiple rows, every row is considered independently when you're talking about conflicts. All right. So this is what happens when you're talking about just two leaders. However, if you have multiple leaders, you have to also decide the topology that you want. So let's say if you have 4 data centers and 4 leaders, there is one approach of taking the circular thing. So this L1 is sending the replication to L2, which is sending to L3, which is sending to L4, and so on and forth. That's one way. The other is the star approach, in which you can say there is some kind of main leader, L1 let's say, and all the leaders are doing the replication using that particular thing, right? So that's one other way, which is the star approach. But the drawback over here is single point of failure. Even if one node goes down, the replication will break. So that's why the third approach is something which is commonly used, which is all to all. Obviously, this is having a lot of data flow, but the time taken for all the leaders to capture the latest values happening across the different data centers in the world, it's quite faster in that sense. So this is something which is pretty much common. MySQL by default comes with circular topology. The problem with all to all, obviously nothing is perfect in this world. So the problem with all to all is the writes may come at wrong order. And let me explain that problem. So let's say there is user A, which is in a data center where the leader is L1, and user B is communicating in a different data center with L3. Let's talk about the same row. So if user A is writing the final value as 50 and L1 responds okay, this write needs to be replicated to L2 and L3. In this case, the replication to L2 is taking a little more time. And meanwhile, the other thing that happens is user B writes 70 and L3 responds okay. And this write of 70 needs to be replicated to L2 and L1. In this case, this replication to L2 happens faster than the replication that was happening earlier with L1. So that's why for L2, it received the write 70 before 50, right? And this is the incorrect order or consistent prefix reads that we discussed with the single leader problem as well. So for a brief duration of time, it had received a write which should have actually happened after this, right? This is similar to the chat problem. So you are seeing the reply first and then the actual question is coming later on. So this is exactly, you can say, a metaphor for the inconsistent order consistent prefix reads problem. So what to do in this case? Well, the exact solution is to use version vectors, and in that what happens is basically we are detecting about the writes that we are receiving across different data centers, and we are giving the different versions to all the writes. So we are combining all the possible values, and whenever we see that there is a new value which is coming, in that case we give it a new version. I'm not going into details of version vectors, but that's something that you can explore. That basically allows us to handle the write and handle the conflicts which are happening across different data centers. At this point, I also want to take a pause and mention that these are complex problems and these are very poorly handled even in today's world. For example, PostgreSQL, the BDR that you talked about, it does not handle the order of writes. It does not provide you any guarantee or handling of those cases. And MySQL Tungsten Replicator is even more bad. It does not even detect conflict detection at all. So just want to mention that these are complex problems, and if you are going into multi-leader scenarios, it's obviously very important to document and test the guarantees that you believe your system is having. So this is very important. Now lastly, I also want to talk about leaderless replication, which is used in Amazon Dynamo, Cassandra, as well as Voldemort. Clients here are directly writing to replicas. There is no concept of leaders. So let's say you are having n nodes in your system. You are putting all the writes to all the nodes. Some might fail and some might succeed. But the idea over here is to achieve better availability so that even if one of the replicas or two of the replicas are down, you don't care. Since you are writing to a lot of nodes and you are reading again from the lot of nodes, you have some algorithm to understand what is the latest write value. So reads are also very, you can say, durable because you are reading the correct value, the last value, which is even when a lot of nodes are down. So this is very robust, and that's why leaderless replication has become very attractive after Amazon Dynamo has started using it. So how it happens essentially is there is some write, which is, let's say, write A, and you send it to all the readers. Let's say the reader 3 is down. Even then, the write is accepted by R1 and R2, which are the replica 1 and replica 2. Now let's say there is some other user who is trying to read this write. Now they are again reading from all the nodes. However, since this node was down, that's still fine. It will give us the old value, but we are getting the new value from the other two replicas. And now you can easily detect that this is the old value and this is the new value. So you read the correct value as well as you detected that R3 is stale and you can fix it, right? So you detected the staleness, that the replica 3 is having a stale value, and you can fix it right away. Or there can be a background process which is running across replicas, seeing or scanning for stale values and updating the replicas with the latest values. So even if your replicas crash or you have scheduled downtime, in leaderless replication, it's quite robust because you can get better availability and durability because there are still other nodes who are processing that. However, this is very important to understand how many writes should be successful and how many reads should be successful for us to have 100% guarantee that we are maintaining the durability and we are reading the latest values and not the stale values. So we can do some math, and let me explain you very easily what happens. So let's say you are having n replicas to which every write or read is communicating. So out of those n replicas, let's say W writes were successful. Now if that is the case, my question to you is, how many reads do you need to be certain that you have read the latest value from at least one node? So let's say there were R nodes from which the read was successful. So n minus R is the number of nodes from which you did not perform the read. And if those many of nodes is less than W, it means that at least one machine is there from which you have performed the read. Okay. So when you performed R reads, there has to be one machine which is having the latest value. This is from simple pigeonhole principle, and you can again replay the last few sentences to understand this. So if n minus r is less than w, it means that there is at least one machine which had the latest write, which means that if you rearrange the terms, r plus w should be greater than n, and this will give us a durability confidence. Now the values n, r and w, these are decided by your system. Generally, if let's say n is 10, usually you keep r and w to be 5 and 5. And if your reads and writes are actually obeying this r and w values, which means that if you are performing, the number of successful reads is greater than or equal to r. Similarly, if the number of successful writes is greater than or equal to w, then those reads and writes are known as quorum reads and writes. So these are giving us better tolerance and availability. And let me give you a very simple example to demonstrate that. So let's say for n is 5, so you are performing a replication. So it means you are performing read and write across 5 machines. And let's say r is 3 and w is 3. So when you're performing this write to 5 machines, let's say 2 were down. So you got 3 successful writes, which is a quorum write. And then when you were reading the value, you read from all the replicas. And now let's say instead of r4 and r5, r1 and r2 were down. So this means that when you were performing the read, different nodes may be down, but still R3 is one machine from which you perform the latest write, right? So you are reading the latest value again. So you can see that when you are doing this read, there were 2 machines down, but 3 were successful. So again, this was a quorum read, which means the data is 100% latest and we have maintained durability. So even when nodes are going down in leaderless replication, you can still handle that, and that's why it has better availability and better tolerance. Alright, I hope you found this video informative, and if that's the case, make sure to subscribe and hit the bell icon so that you don't miss further updates from my side. Thanks for watching, and as always, happy coding. Bye bye.